Hello, can you all hear me? Hello?
Yes, sir.
So my desktop computer has just decided to restart itself. So I was trying to show you the desktop. It has just rebooted on its own. This has that's why there is an interruption. I hope you are all still online.
Yes, sir.
Yes, sir.
Good. Yeah, my computer, like, this never happens, almost, like, very rarely, because it's a Macintosh and Macintosh computers are good like that, right? They don't crash. But unfortunately today my computer has decided to crash, so apologies for that. Okay, so I'm just waiting for the thing to reboot again, then we'll start. Okay, can you all hear me now?
Yes, sir.
Yes, sir.
Yes, sir.
All right, good. Yeah, so it took some time to restart. Right? So start the screen.
Okay. All right. Good morning, everybody. Sorry about that. Not really in my control though. So. Okay. All right. So, okay. Thanks everybody for your feedback. So today, hopefully, I will try to correct some of those issues which you raised, which is that you would like a little bit more physical intuition. So the problem is that to come to that physical intuition, we did need to go through some amount of math, unfortunately, like in the past 4 lectures. But hopefully today we will we are closer to getting that intuition. So. Okay. So what is this intuition that we are looking for? Well, the first thing is, let's see, what did we talk about last time? I had stopped at the point where I was talking about this time evolution of the coherent states, right? And so I'm still visible, right? Okay. So before doing that, let me quickly complete one small derivation, which is this the value of the C naught coefficient, which we have yet to determine. So now that we have this displacement operator, we have shown that the displacement operator generates the coherent state. We can calculate the value of this coefficient C naught, right? So this is equal to 0 d alpha d alpha 0. And since we have the value of alpha, we can write this down. Why? Because so d alpha is exponent minus 1/2 alpha square e to the alpha a dagger, and again there's a minus sign. I believe there is a minus sign that is missing in the what do you call it, the notes that I shared with you, not my notes, the set of typed up notes that I had shared with you. So, yeah, right. So it should be alpha a dagger exponent minus alpha star. So this minus sign over here, this one is not there in those notes. Okay, so now we can use this we can calculate this explicitly. And the way you do that is that you take this exponential, for example, this term, and you Taylor expand it, right? So the first term is the identity, the second term is alpha star a, and then the higher order terms are all of order alpha star square, alpha star a square, and higher terms, right? But now you can see that in this expression, what you have is you have this exponential operator acting on 0, right over here, this part. So this is equal to 1 minus alpha star a plus other operators, other powers of a acting on 0, right? Now, we know that a acting on 0 is 0. So this means that a square acting on 0 will also be 0. And any power of a acting on 0 will be 0. So when I look at the action of this operator on 0, all of these terms which have a in them will give you 0. So the only non-zero term will be the identity. That will just give me 0. So exponent of minus alpha star a acting on 0 will give me 0. Okay. So I can put this in here now. Then that leaves me with exponent minus alpha square by 2 and then I have one more term, this exponent of alpha a dagger. So I have 0 exponent alpha a dagger 0. Okay. Now the difficult way to solve this would be, well, I mean, it's not difficult either way, it's the same. So again, we take this a dagger and we expand it in an exponential series. right? So we get different powers of A. Now, what does this operator do when you act on 0 on the left, right? So when you act on the ket 0, you'll get 1 plus A dagger plus A dagger square 2 5. All of that acting on 0. Now the identity operator acting on 0 will give me 0, right? A dagger acting on 0 will give me 1. A dagger square will give me 2, and so on, right? So I'll get something like not bothering about the coefficients and so on, right? 1, 2, and so on. Now on the left, I have the 0 bra, right? So when I contract the 0 bra with this, what happens? I get 0, 0 plus this 0 bra is contracted with all of the components which contain 1, 2, and so on, right? And all of these are going to vanish, right? Because these are orthogonal states. So this tells me that C naught, right? So exponential of alpha acting on 0 will again give me 0. Sorry. Exponential of alpha acting on 0 will give me 0 plus all of this. But when I contract it with 0, so contraction is a term that is used for when you take inner product, right? It's the same thing. You will get 0, 0. So C naught will be exponent of minus 1/2 square by 2, 0, 0. And this is just equal to the number 1. So finally, we have our expression for C naught. Okay. Once we have this expression, we can use this to write down the complete expansion for any coherent state. So an arbitrary coherent state, let us remind ourselves, it looks like this. It's a alpha to the nth power and root of n factorial and n, right? So you just get a factor of this C naught in front. Root of n factorial times. So this is the definition of this is the coherent state in the number operator basis, right? So we know all of these quantities. Alpha, as we know, is just a complex number, right? And n is the number operator eigenstate. So once we have this, we can do other calculations, more physical calculations, right, to give us better insight on what this coherent state represents. Okay. So as an example of what does it represent physically, right? So you imagine that you have a coherent state of light, right? Coherent state of photons, okay, alpha. And then you ask the question that that if I make a measurement of this coherent state, right, what is the number of photons in alpha, right? Now, alpha consists of a superposition of the number states, right? N. And what is this N, right? This N, so if you think in terms of, if you think in terms of photons, for example, so what is N? N consists of N quanta, each carrying energy h bar omega, right? And so if you have a laser, right? Laser at frequency omega, or at frequency f is equal to 2 pi omega, right? Then this is the quantum state represented, which represents this kind of a system, is a coherent state. And then in this coherent state, I can ask that if I make an observation of the intensity of this laser, right? If I measure the intensity of the laser, that intensity will tell me if you measure the intensity, what is intensity? Intensity is the power per unit area, right? So you measure the intensity, and when you measure it in some, so your laser is, these are your light waves. It falls on some surface, right? And when it falls on your surface has some area, let's say delta A, and you make a measurement. Your measurement also lasts for some duration, right? It's not an instantaneous thing, right? So for some duration, delta T, right? Like for example, you switch the laser on and off, or whatever your detector is that is counting the photon, it will have some on time and some off time. It will not happen instantaneously, right? So during the time that measurement happens, what will you get? You will get intensity times area, which is power, right? And then what is power? Power is energy per unit time, right? So multiplied by time. This gives you energy, right? And what is the energy? The energy is equal to the number of photons measured by the detector multiplied by the energy of each photon, right? So if you measure, so then that tells you that N, the number of photons that you measure, is given by the intensity of the laser multiplied by delta A multiplied by delta T divided by h bar omega. Right? Now what will happen is that every time you make the measurement, let's say you keep delta A and delta T fixed, and you repeat the process, you repeat the measurement. Each time you will measure some value of N, right? So what will you get? So after repeated measurements, with fixed delta A, delta T, and the intensity is fixed because we are not changing the system, and we are not changing the laser also. So the frequency is also fixed. right? So this it's the same quantum state, but after repeated measurements with the fixed quantum state, right? What will you get? You will get P of n. What is P of n? This is the probability distribution for number of photons, right? So now we know that, so what is this P of n going to be? Well, we know that alpha is equal to C of n times n, right? So if I ask what is the probability of n, then that probability P of n is what? It's just C of n squared, right? And so what is this C of n squared? C of n squared is this quantity, right? And I'm using capital N and small n. I should use maybe small n here for the photon number. So, yeah. Okay. And this we can read off from the expression. From this expression, we can just read off what C of n is going to be. So P of n is equal to exponent minus alpha squared times the squared amplitude of this guy, which is alpha to the power 2n divided by n factorial. Let me put that on a new page. So we have Cn, just write it again, is exponent of minus alpha squared by 2 and then alpha to the power n root n factorial. So P of n is equal to C of n squared, which is exponent of minus alpha squared by 2 times right, this thing multiplied by its own complex conjugate, which will give me alpha star to the power n times alpha to the power n, and this whole thing will give me exponent of minus alpha squared by 2 alpha squared times n divided by n factorial. This is P of n. So we put a nice box around that also. Now, okay. Fine. So this is the probability distribution for n. But now the thing is that we would like to be able to express this in terms of the number of photons that are actually measured. So the number of photons that is measured which is the expectation value of n, right? So this is P of n. Here, this n without the bar is the n measured in one instance of the measurement. So every time you do the measurement, you get a different value of n. But then there will also be a mean number of photons that is measured. So if you average over all the experiments, you will get a mean number of photons, right? What is this mean number of photons going to be? This mean number of photons is just going to be the expectation value of the number operator. Right? So the small n is the eigenvalue of the number operator that is measured in each repetition of the experiment. And if you average over all the experiments, you get the mean number of photons measured, which is this quantity. This mean number of photons we can evaluate as A dagger A alpha, right? And now alpha is an eigenstate of A, so this just becomes alpha squared. Okay, so you'll get alpha from here and alpha star from here, so whole thing will become alpha squared. So this gives us a physical meaning of alpha, first of all. Okay, so this corresponds to the power of the average power of the laser. So if you increase or decrease the laser, what you are doing is you are increasing or decreasing the amplitude of alpha. And now we can substitute this expression alpha squared, the mean value n. So I can write down P of n in terms of the mean value of n. So I'll get P of n is equal to exponent minus times e to the minus, right. So wait a minute, 1 second.
वहाँ पे e की पावर माइनस एक्स स्क्वायर का स्क्वायर होगा तो वो माइनस एक्स स्क्वायर रह जाएगा ना, माइनस अल्फा स्क्वायर e की पावर माइनस अल्फा स्क्वायर.
एक सेकंड भैया, मैं क्या गलती कर रहा हूँ जरा देखने दीजिए ना. Given by alpha to the 2n e to the minus alpha square.
सर वो 2 नहीं आएगा नीचे एक्सपोनेंट के अंदर अल्फा स्क्वायर के नीचे.
हाँ नहीं ठीक है, हो गया सही है. हाँ ये 2 नहीं आएगा, सही कह रहे हैं आप. थैंक यू. 2 नहीं आएगा because you are taking the square, right? Thank you. So you will get exponent of minus n, and then this quantity can be written as, this quantity can be written as mean value of n to the power n divided by n factorial. So what is this? This is also known as a Poisson distribution. So this is called a Poisson distribution. Right? So if you want to write this out in a little bit slightly different way, you can write it like instead of n, if you want to use the variable x, let's say. So this is x, this is p of x. Poisson distribution, what is it? It's exponent of minus. So let me call it alpha, not alpha, because alpha will confuse it. So it is some constant here, okay? Some constant times the mean value of x to the power x divided by x factorial. Now, you know that there is also something called the Gaussian distribution, right? We have seen that before. So Gaussian distribution is 1 over root something 2 alpha e to the minus x squared by alpha, where here now alpha is the standard deviation, right? So if you look at the Gaussian distribution as an example, what does that give you? That gives you xp of x. The Gaussian distribution looks like this, right? And the Poisson distribution looks like this. This is the Poisson distribution. Now, what is the interpretation of the Poisson distribution? Is that if you take a collection of some items such that the probability of getting an item from that collection is given by some fixed number, and you repeatedly pull out items from that collection, then the resulting probability distribution is given by the Poisson distribution. So this describes any process in which there is a there is particles or any item is distributed uniformly with some density, let's say alpha squared, in this case alpha squared. That is the mean number of photons, right? So that is what this Poisson distribution is. Okay, now, so what have we talked about? We talked about what the coherent state leads us to. One of the questions that you might have is that when we talked about the coherent state, we defined the coherent state for a single harmonic oscillator. And now suddenly I'm saying that we can use the coherent state to describe a beam of light. But then you will think that, well, a beam of light is not a single particle, right? It's a collection of many particles. So how can I describe that with the same state as I used to describe a single harmonic oscillator? And so the reason for this, right, is basically that you're talking about photons, and photons are bosons, right? So we will see later on, we haven't talked about bosons and fermions yet, but I mean, I presume that you have obviously encountered these things in your undergraduate studies. What is the property of bosons? Bosons have the property that they can all be in the same state at the same time, right? So I can have n photons all with exactly the same energy, right? Let's say h bar omega. They can all be in the same state, right? So you can think of each photon. So each photon is a separate harmonic oscillator, right? So you think of a laser. A laser is composed of many photons. Okay, there are many photons. And each photon corresponds to a single harmonic oscillator. So this is the harmonic oscillator potential, let's say. This is just to schematically, right? But because photons are bosons, right? All of these n photons which have the same energy, they all correspond to the same state of the harmonic oscillator potential, which is some energy state. All of these are equivalent to having a single harmonic oscillator with n photons in this state, in whatever this energy state is. So you have one photon here, one photon here, one photon here, one photon here, and so on. right? And what is n times h bar omega? That corresponds to the nth excited state of the harmonic oscillator. So each photon you can think of as corresponding to the ground state, the zero state. And when you look at n of them, that corresponds to having the nth excited state of the harmonic oscillator. So this is like 0, right? So each photon has, but when you combine all of them, you get something which has a total energy which is given by, which corresponds to the nth state. And n photons all with exactly the same energy is equal to a single state with total energy h bar omega times n. And this is also the reason that you can have lasers in the first place, right? So a laser, what is it? It's basically it's a Bose-Einstein condensate. A Bose-Einstein condensate of photons, right? And if you have looked at what Bose-Einstein condensation, what happens? So in that case, you will. I'm just going to mute. Okay. All right. So this is the reason. So it is described. So that is what we mean by a coherent state. A coherent state means you have many systems, right? And they all condense into a single state. That is also another example of the meaning of the word coherence, right? Coherence means to be in phase, right? So what is a laser? A laser is basically lots of different light waves, all of the same frequency, of energy h bar omega, and all exactly in phase. Because if they are out of phase, then you will get destructive interference, right? But instead, in a laser, you have completely constructive interference. All of them are exactly in phase. So they all cohere, right? Okay. So this is the one physical aspect of coherent states, okay? The other physical aspect is the fact that if you look at the time evolution of coherent states. So do you guys have a class right now?
No, sir.
Okay, so I'm going to take another 10 minutes, okay? So if you look at the time evolution of coherent states, so we have this is our alpha. Again, alpha is e to the minus alpha squared by 2 summation of alpha to the power n by root n factorial. So this is the state at a certain time, at time t is equal to 0, let's say. Okay. So then we can ask, what is alpha t? That is, what is the state of the system at a later time, right? Now, to find out the state of this system at a later time, what we do is we can use Schrodinger's equation. What is Schrodinger's equation? It tells us that h psi is equal to I h bar d by dt psi, right? This is Schrodinger's equation. Now, what is psi is some arbitrary state, and I can take any arbitrary state and expand it in terms of the energy eigenstates of the system, right? And what are the energy eigenstates? The energy eigenstates are just the number operator states, right? Number operator states are the eigenstates of the Hamiltonian, because the Hamiltonian is just the number operator plus 1/2 multiplied by h bar omega, right? So first I can ask, how does what happens to the time evolution of a single eigenstate? So let me ask, what happens when psi is equal to just one n, some given value of n. Okay, so only one coefficient is non-zero, all the other coefficients are zero. So now in this case, what is h bar? What is h hat acting on n? H hat acting on is h bar omega a dagger a plus 1/2 acting on n. Right? What is this? This is just h bar omega times n plus 1/2 acting on n. And what is this? This is E of n. This is the energy of that state, right? So finally, we have this. We have E of n, right? So h of n is an eigenstate of h. So we can just write it as the eigenvalue is equal to I h bar d by dt. So this equation is telling us that if I take the time derivative of n, I get n multiplied by itself, right? And this has a very simple solution. What is this? This tells us that n of t is equal to exponent En, right, minus IEn by h bar times t times n of 0, right? So the only change that is happening in the state is essentially a stationary state. It's an eigenstate. The only thing that happens is that each one of the coefficients of the state is multiplied by the same constant phase factor. Okay. So this is the time evolution of a single number operator state. There is just one. So n of 0 is just n. I'll just write it as n. And n at a later time t is simply this phase factor multiplied by n. That's it. So the system stays in the same state with just a rotating phase. But now if you ask what happens to an arbitrary state, and an arbitrary state which is a superposition of these number operator states, each one of these states will itself remain in the same state but with a constant phase, constant rate of change of the phase. But that rate of change of the phase is different for each state, right? So what happens to psi of t? Psi of t can be written as C of n exponent minus I E of n t by h bar acting on n, right? So each state is just multiplied by a phase, but this phase is different for each state, right? Because E of n keeps changing. So now, so this tells us what the time evolution of the state looks like. Now we can write this in a slightly different way, psi of t, we can call this whole thing Cn times this as Cn times t. So what we are saying is that it is this coefficient that changes with time. Okay. Now, in the case of a harmonic oscillator, in the case of a coherent state, for example, for alpha, what is C of n? C of n we know, exponent minus alpha square by 2 alpha to the power n by root n factorial. So what happens to this after a certain time t? This just becomes C of n times e to the minus I h minus I e n t by h bar. Is just multiplied by this phase factor. Okay. Now we can use this result to do certain calculations. For example, we can calculate the expectation value of the position operator. Now you know that the expectation value of the position operator in the number operator eigenstates is 0. Right? But if you ask what is the expectation value of the number operator in the coherent state, this will not be 0. Okay. So we will ask what is this quantity. So first we will ask what is x of 0. X of 0 is the initial position, that is this quantity. Then we'll ask what is x of t, which is the expectation value of the position operator at a later time t. Okay. So what does this become? This becomes basically, let me just see, it's coherent. Okay, this I will leave for you to work out as part of homework number 5. Okay. So you know what the x operator is. X operator is 1/2 a plus a dagger. You know what this alpha is. You know what alpha t is. You can calculate this. And what you find is that x of t can be written as some x naught times cosine omega t, and then there is some phase factor. So I should put a bar on this because these are all expectation values. So this tells me that if I have a coherent state, the position goes like this. And similarly, if I calculate the momentum, the expectation value of the momentum at a certain time t, I'll get the sine term. Okay. All right. So I think this is it. As far as coherent states are concerned, I won't spend any more time on this because I think you're all sick of coherent states. Okay. So I'll stop here. There are many more interesting things one can do. So in the next class, what I will do is I will start talking about, I will talk about this thing, the correspondence principle, and something called Ehrenfest theorem. And then there we will apply there we will see how coherent states satisfy the correspondence principle. Okay. All right. So that's it. For today, I'll stop here. Any questions? When is your midsem, by the way?
Sir, some teachers are saying first week of December, but we don't know the dates or something.
Okay. All right. Then I'll plan on holding your quiz sometime next week. Okay. And I'll let you know one day in advance when that is going to be.
Sir, like, will there be a proper date sheet for midsems or like
Yeah,
teachers?
of course. Of course.
So approximately like when will be getting that date sheet?
I can tell you, I have the schedule. One second. So your classes started on September 28th, right? Yeah. So
5th November, so 5th October, sir.
5th October. 5th October, right? Let me. So I'll just share this calendar with you on Telegram. Okay.
Sir, is it that weekly calendar like with everything?
Yeah, basically.
But I'm asking like a proper date sheet just for midsems, like this subject midsem is on this date.
That you will probably get next week. Okay. Why do you need to do some astrological preparation? Hello.
Yes, there was an aeroplane going so much fast.
नहीं, मैंने कहा आपको कुछ शुभ मुहूर्त निकालना है किसी सब्जेक्ट का.
No, not sir. No, sir.
I mean, like whatever it is going to be, right? Like something is going to be sooner, something is going to be later, but it will all be in the first week. So next week is the last week of November, right? So we'll probably have our quiz. Let's fix November 25th, Wednesday, as the date of our quiz. Okay.
Okay, sir.
And that day, homework number 5 will also be due for submission. All right. So if there are no questions, are there any questions? Probably not. Okay. All right, then I'll end the. Shall I end the meeting then? Anybody else? Any questions at all? नहीं, कोई question? ठीक है, okay. All right. Then. All right. I'll see you all tomorrow. Okay. Okay. Bye.
Thank you, sir.